All right, welcome to This Explainer. Today, we are going to decode something that honestly sounds like pure magic, but it is very, very real. We're talking about the invisible heartbeat. Specifically, we're diving deep into a fascinating new research paper that introduces an AI framework called PhysFlow. And what this research proposes is a way to read highly accurate vital signs using nothing more than an everyday video camera. You heard that right. No smart wearables, no awkward finger clips at the doctor's office, just a standard camera lens. So how exactly does that work? Let's get right into it.
So I have to ask, can your webcam actually read your heartbeat? I know, it sounds exactly like a hook from a futuristic sci-fi movie, but I assure you it's absolutely not. In fact, this is a highly active, incredibly competitive field in medical AI research right now. Think about it. The camera sitting on your laptop or your smartphone right this second is theoretically totally capable of capturing the microscopic physiological changes happening in your face with every single pulse of your heart. But here's the catch. Doing it accurately out in the messy, chaotic real world, that is a massive computational challenge. And it's exactly the bottleneck that PhysFlow was built from the ground up to solve.
So, here is our roadmap for today. We'll be looking at 1. The invisible heartbeat. 2. The real-world noise problem. 3. Divide and conquer. 4. Dual-field rectified flow. 5. State-of-the-art results. And finally, 6. The future of health tech. Let's jump right in.
Section 1. The invisible heartbeat and the science of remote photoplethysmography, or rPPG. Okay, to really understand the genius behind PhysFlow, we first need to quickly define the foundational science that makes all of this possible in the first place. The technical term is remote photoplethysmography. Yes, it's a mouthful, so we usually just call it rPPG for short. So what actually is rPPG? Well, it's a completely contactless sensing technique. It basically estimates your blood volume pulse simply by analyzing these super subtle color variations in videos of your face. Here is the underlying physiology, which is super cool. Every single time your heart beats, it pumps blood through those superficial vessels resting right beneath the skin of your face. And this microscopic change in blood volume actually slightly alters the way your skin absorbs and reflects ambient light. Now obviously, these variations are totally invisible to the naked eye. You literally cannot see them when you look in the mirror. But a standard digital camera sensor, it can actually capture these incredibly tiny fluctuations in pixel intensity. So, if we can isolate those specific pixel changes, we can reconstruct the actual pulse. Section 2. The real-world noise problem. Essentially, when the magic fails. Now, if the underlying science is really that straightforward, you might naturally be wondering, well, why isn't my laptop already doing this perfectly right now? Well, the core issue preventing this tech from working flawlessly on every device is everyday environmental noise. You see, the variations in light caused by our pulse are incredibly weak. If you're sitting perfectly, rigidly still in a lab with highly controlled, stable lighting, sure, older rPPG algorithms actually work pretty well. But out in the real world, we have severe illumination changes. Literally just a cloud passing over the sun outside your window completely changes the lighting on your face. We have unconstrained head motion. You nod, you turn to look at your phone. And we have rich facial expressions. You smile, you frown, you blink. All of these completely normal everyday occurrences create massive amounts of visual noise. And this noise completely overwhelms those tiny invisible pulse signals. I mean, the visual changes caused by a simple smile are orders of magnitude larger than the microscopic color shift caused by a heartbeat. So the absolutely crucial point here is how the AI actually deals with all this incredibly messy data. Most existing deep learning methods out there use what we call unified modeling. They basically try to process all the tangled, messy data, the pulse signal, the lighting changes, the sudden head movements, all at once in a single massive end-to-end process. But because the pulse signal is so incredibly weak, it just gets completely drowned out by all those strong disturbances. The AI basically loses the heartbeat entirely in the noise. It's like trying to hear a pin drop in a crowded room. Now, PhysFlow takes a totally different and much smarter approach called frequency-decoupled modeling. Instead of tackling the tangled mess all at once, PhysFlow actively separates the signal right from the start to dramatically reduce that interference.
Section 3. Divide and conquer. How we go about separating the signal.
And this brings us to the brilliant divide and conquer strategy the researchers use to actively isolate the heartbeat from all that chaotic visual noise. To make sense of it all, the researchers applied a frequency domain decomposition strategy. Now, the easiest way to think about this is like a piece of music. If you want to isolate elements of a really complex song, you might separate the heavy, slow, thumping bass line from the fast, high-pitched treble notes, right? Well, PhysFlow does exactly this, but with the heartbeat signal. It breaks the signal down into two highly distinct parts, the trend component and the amplitude component. The trend is like your bass line. It captures the slow, low-frequency waveform profile and things like baseline drifts over time. The amplitude, on the other hand, is the treble. It represents the extremely fast, fine-grained, actual pulse variations that spike with every single heartbeat. By completely separating these two elements, the AI doesn't get confused trying to learn one giant, impossibly messy pattern. Section 4. Dual-Field Rectified Flow. Let's look under the hood of PhysFlow. Okay, so now that the signal is nicely separated, how does the AI actually process it? Let's literally lift the hood on PhysFlow and look at its engine. What's really interesting about this architecture is how it moves the data. Because we have two totally separate signals, the trend and the amplitude, PhysFlow uses two completely separate processing engines, which the researchers call velocity heads. On the left side of the diagram, we have the trend head. Because the trend is a slow, global waveform, this head uses spectral bases and a low-pass filter to explicitly favor smoothness. It deliberately suppresses any jerky, high-frequency noise. It is built entirely for stability. Then on the right side, we have the amplitude head. Now this head is aggressively looking for those extremely fast, subtle pulse variations. So it uses condition-aware temporal predictors and dilated convolutions to capture highly sensitive, fine-grained temporal dependencies. They explicitly treat the slow trend and the fast amplitude as two completely independent tasks, and that cuts down mutual interference dramatically. Which naturally brings us to the actual rectified flow part of the PhysFlow name. Now, if you know anything about traditional diffusion models, like the ones used to generate AI art, like Midjourney or DALL-E, you know they take pure static noise and slowly, painfully denoise it over dozens or even hundreds of steps to create a final output. It works beautifully, but it is incredibly slow. Rectified flow is a much newer, highly efficient mathematical approach. It essentially finds the absolute straightest, shortest path between pure Gaussian noise and the true data distribution. So during inference, which is when the model is actually running and predicting your heartbeat, it initializes with random noise. Then it uses the trend and amplitude heads we just talked about to predict the velocity or the exact direction to move the data. Using just a few simple Euler ordinary differential equation, or ODE steps, it rapidly evolves that static noise straight into a remarkably clean, accurate rPPG output. It is just incredibly fast and computationally efficient.
Section 5. State-of-the-art results. Because eventually, the data has to speak for itself.
Okay, we've seen the underlying theory and we've explored the architecture. But does this dual-field, decoupled approach actually work better than everything else currently out there? Well, the leap in performance here is genuinely undeniable. This data is pulled directly from Table I in the research paper. We are looking at the root mean square error, or RMSE. And in this case, obviously, a lower number is better. We're specifically comparing PhysFlow against the previous reigning state-of-the-art model, which was called PhaseNet, across two incredibly difficult, challenging datasets. First, VIPL-HR. This is a massive dataset absolutely full of diverse head motions and crazy, unpredictable lighting conditions. PhaseNet scored a 6.37 error rate. PhysFlow crushed it with a 5.79. Then we have BUAAMIHR, which is a benchmark specifically designed for low illumination conditions, literally trying to read heartbeats in the dark. PhaseNet scored a 1.43, but PhysFlow dropped that error all the way down to an impressive 1.17. Across the board, no matter the conditions, PhysFlow achieves the lowest error rates.
But let's look at how this builds a really compelling visual case for accuracy. Look at these scatter plots. They're comparing the predicted heart rate on the y-axis to the ground truth actual medically verified heart rate on the x-axis. The black dashed line right down the middle is the identity line. That represents a perfect, flawless prediction. Now the plot on the far left is PhysFlow. Notice how incredibly tightly clustered those dots are right along that center line. Now compare that to PhaseNet in the middle and Rhythm Former on the far right. You can clearly see significant scatter, widening out, and obvious bias in those older models. PhysFlow is simply locked in. And if you look at the bottom row, those are bland Altman plots, which essentially measured the limits of agreement. Once again, PhysFlow has a much narrower band, meaning it yields a significantly smaller estimation bias and proves to be far more stable across a huge variety of different human heart rate ranges.
Now, getting accurate heart rate numbers is great, obviously, but the actual shape of the waveform matters immensely for real clinical health monitoring. And this is a super powerful show, don't tell moment straight from the paper. On the top left, we can see PhysFlow's reconstructed waveform in orange, plotted directly against the true medical ground truth in blue. It traces it almost perfectly. It preserves the exact morphology and the temporal phase.
Now look over at PhaseNet and Rhythm Former. Their orange lines show really messy local distortions, irregular random fluctuations, and they completely lose the temporal phase. Furthermore, look at the power spectral density, or PSD plots on the bottom. PhysFlow has one incredibly sharp, dominant peak exactly at the true heart rate. The other methods, they exhibit massive spectral dispersion and a bunch of spurious, messy peaks. So PhysFlow isn't just getting the final number right, it is reconstructing a phenomenally faithful, highly accurate physiological signal.
Section 6. The future of health tech, speed, and most importantly, practicality.
So, we know for a fact that PhysFlow is the most accurate model. But here's the reality. Accuracy in a perfectly controlled lab setting just isn't enough to change the world. We need to shift our focus to the real-world impact of this breakthrough and why this matters for the actual consumer devices sitting on our desks and in our pockets. 63.74 caps. That stands for over 63,000 frames processed per second. Because PhysFlow utilizes that incredibly streamlined rectified flow process, completely avoiding the heavy, slow, iterative steps of traditional diffusion models, its throughput is absolutely staggering. It is explicitly built to handle real-time applications without breaking a sweat.
If we look at the inference time comparison pulled straight from Table IV in the study, the real-world practicality becomes totally obvious. PhysFlow requires just 13.63 milliseconds of inference time. That beats Rhythm Former at 14.41 and absolutely crushes PhysDiff at 16.60. And what's more, the paper notes that PhysFlow consumes significantly less memory. We're talking only 614 megabytes compared to the thousands and thousands of megabytes required by those older methods. It's not just the most accurate, it is incredibly fast and remarkably lightweight. This means it can actually run efficiently on everyday edge devices, like your standard smartphone, your laptop, or even a car's internal driver monitoring system, all without draining the battery in 10 minutes or causing massive system lag.
To really summarize the core triumph of this research, I think we should just look to the author's own definitive conclusion. They state, PhysFlow outperforms state-of-the-art methods in both heart rate estimation and rPPG waveform reconstruction across diverse, challenging scenarios. By recognizing that you simply can't treat all video data the same, and by intelligently separating the slow waveform trends from the lightning-fast pulse amplitudes, they've effectively solved one of the single biggest bottlenecks in contactless health monitoring today.
Which leaves us with a pretty profound thought about tomorrow. We already use facial recognition every single day to unlock our phones and our laptops, right? The camera's always there, and it is always looking. With the sheer accuracy and breakneck speed of frameworks like PhysFlow, we are rapidly approaching a reality where continuous, totally invisible cardiovascular monitoring is simply a built-in, default feature of our digital lives. No smartwatches you have to remember to charge, no uncomfortable chest straps you have to wear to the gym. So my question to you is, are you ready for a world where your everyday devices monitor your health just as effortlessly as they scan your face? It's an absolutely fascinating future to think about, and the foundational technology to get us there is already being written. Thanks for joining me on this explainer, and I'll catch you next time.